In this video, we present techniques for solving radical equations with a variety of examples to illustrate. What do we mean by a radical equation? A radical equation is an equation that contains a variable and a radicand. Let's consider a variety of examples. Notice that in each example equation, there is a variable and a radicand. The radicand might also contain other terms, and the radical term may be isolated on one side of the equation or have other terms attached to it. We can have radicals on both sides of the equation and even have radicals under radicals. All of these constitute what we refer to as radical equations. To solve radical equations, it's helpful to have some general guidelines to follow. First, rewrite the equation so that the radical expression is isolated on one side of the equation. If there is more than one radical expression, separate them on opposite sides of the equation. Then raise both sides of the equation to the same appropriate power. An appropriate power is one that would eliminate the radicals, as we will see in our examples. Next, combine like terms on both sides of the equation. If the equation still contains one or more radical expressions, repeat the previous three steps. When there are no more radical expressions remaining, solve the resulting equation for the variable. Finally, check all solutions in the original equation for extraneous solutions. An extraneous solution is one that arises in our solution technique but does not satisfy the original equation. Recall that some algebraic processes have the potential to introduce such extraneous solutions. Multiplying both sides of an equation by a variable or raising both sides to a power can introduce extraneous solutions. Now let's solve the 5 example problems. First, solve the square root of the quantity x plus 4 equals 6. For our solution, we start with the given equation and notice that the radical expression is already isolated. We then square both sides of the equation to eliminate the square root. We get an equation without radicals and solve that equation using our prior techniques. Because we squared both sides of the original equation, it is essential that we check x equals 32 in the original equation. Square root of x plus 4, we substitute 32 for x, get square root of 36, which equals 6, and this checks in the original equation. Therefore, x equals 32 is the solution. Next, let's solve the equation the cube root of x plus 10 equals 8. This time the radical expression is not isolated. We subtract 10 from both sides to isolate the radical, then cube both sides, so x equals negative 8. Again, we need to check this in our original equation. The cube root of x plus 10 equals the cube root of negative 8 plus 10. The cube root of negative 8 is negative 2. We add 10. We get 8, which equals the right-hand side of the equation. So this checks in the original equation, and therefore x equals negative 8 is the only solution to the equation. For our third example, consider the equation square root of the quantity 17x minus 2 equals x plus 4. The given equation does have the radical expression isolated, and we want to square both sides to eliminate the square root. We have to remember that to square a binomial means to multiply it by itself using the distributive law or the FOIL method. Now we have a quadratic equation to solve. We put the quadratic in standard form and factor to get a product equaling 0. Thus, one of the factors must equal 0, so x equals 3 or x equals 6. We have to check both of these values in the original equation. First, we verify that x equals 3 checks. Then we verify that x equals 6 checks. Therefore, the solution is x equals 3 or x equals 6. Now we'll consider an example with two radical expressions. Solve the equation square root of the quantity 3x plus 1 equals the square root of x plus 1. Notice that in one radical expression the plus 1 is in the radicand, but in the other expression plus 1 is not under the radical. These two radical expressions are already separated. We need to square both sides to eliminate square roots. On the left-hand side of the equation, the square root is eliminated. The square root radical is eliminated. But on the right-hand side, we need to expand or FOIL the two binomial expressions. Thus we get 3x plus 1 equals x plus 2 square roots of x plus 1. We still have a radical expression, so we need to isolate it and square again. We subtract x and 1 from both sides of the equation and get 2x equals 2 square roots of x. Divide both sides by 2 and we're ready to square both sides of the equation. This produces a quadratic equation that we put in standard form and factor to have a product equal to 0. Setting each factor equal to 0 and solving each resulting equation produces x equals 0 or x equals 1. It is readily verified that both of these values check in the original equation. Therefore, our final solution is x equals 0 or x equals 1. For our final example, let's solve the equation the square root of the quantity 2 minus root x equals root x. Notice that although we have nested radicals on the left-hand side, the radical expressions are as separated as possible. Squaring both sides will eliminate the outer radicals on each side. We still have a radical expression in our equation, so we need to isolate that expression before squaring both sides again. We add the square root of x and subtract x from both sides. Now we can square both sides to eliminate the remaining radical. Notice that to compute 2 minus x squared, we get 4 minus 4x plus x squared. We put the resulting quadratic in standard form, factor, and set each factor equal to 0 and solve for x. We get that x equals 1 or x equals 4, and we must check each value in the original equation. When x equals 1, the left-hand side of the equation equals 1, and the right-hand side of the equation equals 1 as well. Therefore, x equals 1 checks in the original equation. When x equals 4, the left-hand side of the original equation equals 0, but the right-hand side equals 2. Thus, x equal 4 does not check in the original solution. Therefore, the only solution to the original equation is x equals 1. We should note that it is also possible for neither value to check, resulting in the original equation having no solution.